Okay, so today we're gonna be talking about an introduction to the neutron log. So what is the neutron log? So the neutron log, this is a log. It's a porosity. It's a log of porosity, and it's based on the effect of the formation on like fast neutrons emitted by a source. So we have a source that is emitting certain types of neutrons at high speed, high energy, and when these neutrons interact with atoms in the formation, they are going to get absorbed and they're going to lose energy. Okay. So now, when these hydrogens are interacting with the atoms, right? Then the absorption is going to happen, and the losing of speed and energy is going to happen, and there's going to be some gamma rays produced. There's going to be some of them are going to get absorbed. So the count rate that we're going to get is going to differ based on how much absorption how much neutrons are we losing in the process. So hydrogen has by far the biggest effect in slowing down and capturing neutrons. Okay, so why, again, just to review these neutrons with high energy, when they get introduced into the formation, they undergo an effect that is called scattering, and they produce high energy gamma rays in the process. Okay, they lose energy, but they produce high energy gamma rays. But we need to understand why the hydrogen is the element that is affecting the neutrons the most. So when fast neutrons interact with the nuclei of atoms within the formation, this interaction is like the process that goes in the interaction is called like elastic scattering, and it involves the neutrally charged neutrons and a stationarily positively charged nucleus. Okay, in each interaction or in each collision, the neutron is going to lose some energy and it's going to slow down. Okay, and the nucleus of the atom is in the formation is going to gain energy. So the neutron is losing energy, the atom of the formations are gaining energy. So these collisions are going to happen with all the different nuclei of all elements in the formation. However, the process of energy transfer, energy loss from neutrons, is most efficient when the masses of the neutron and the nucleus are the same. If we have the same masses between these elements and they collide, the losing of the energy is going to be more effective. But if you have a little neutron colliding with a bigger particle, this process of losing energy is not going to be as effective. Okay, so this is why, I mean, hydrogen nuclei hydrogen is the lightest element. The neutron has approximately the same mass as hydrogen nuclei. So this is why, because they have the same mass or approximately the same mass. This is why in this plot we can see how the energy drop, the slowing down of the slowing efficiency of hydrogen is greater than silicon and oxygen atoms when we see it as a function of energy, in a clean sandstone. So in a clean sandstone of 15% porosity, we can see that that is the hydrogen which is the one that is making more impact to the slowing down of efficiency. Okay, so now when the neutron tool is releasing these fast neutrons, okay, they are, of course, with high energy, with high speed, but in just like a little time, like let's say microseconds of, a solid material being exposed to this fast neutron source, the formation already slow down the incoming neutrons down to the different stages of that neutrons go through. So for example, the first one that arrive are the fast neutrons, but then as the neutrons are colliding, losing energy, losing speed, they become like intermediate neutrons, epithermal neutrons, and then just a cloud of thermal neutrons, which are the neutrons that have very small energies that are associated with just the random kinetic motion that is associated with just room temperature. So, and these ultimately get absorbed by the nuclei in the okay. So this neutron absorption phenomena, this thermal and to some extent the epithermal neutrons can be absorbed by the nuclei of the formation atoms. And the efficiency of this neutron absorption, as we said before, it varies from element to element. But as we said before, hydrogen is very important in this process, but there's also another element that also exhibit like significant neutron absorbing behavior, which is chlorine. So if we have and these elements exist in rocks, in reasonable quantities. So if we have hydrogen and chlorine, we can see this absorption happening, like we can see in these equations. And in neutron logging, some tools measure the epithermal neutrons, some others measure the thermal neutrons, and actually some other tools measure the gamma rays emitted by the emitted when a neutron is absorbed. Some gamma rays are emitted, and this is what they measure. Again, as the reason why this tool is called neutron porosity, because the hydrogen is mainly located in the hydrocarbons and in the water, which is occupied in the pore system, right? The pore space. So this is where, so if we have a rock that has a lot of pores with water, we're gonna have more hydrogen interacting with the neutrons. So we need to find a way to have an idea of how much hydrogen we have in our zones or in our material or the information that we're analyzing. We can see this concentration of hydrogen in two ways. You can see it from a mass basis or from a volume basis. So if you see it as a mass basis, for example, so what we can do is in the numerator we can have, for example, the mass contribution of hydrogen, and in the denominator we can have the total molecular mass, so the sum of all non-hydrogen elements plus the hydrogen contribution, and this is going to be a concentration based on mass, okay. But the neutron tool investigates a volume of formation, so not a unit mass of formation. So as it is emitting neutrons into the rock, the response depends on how many hydrogen atoms are present in the tool's investigation volume. So we need to convert from hydrogen per unit mass into hydrogen per unit volume. So in order to do that, we have to multiply by the bulk density. So basically the mass concentration tells us the proportion of hydrogen in the material based on the chemistry, but the neutron log is responding to the number of hydrogen atoms inside a volume of rock. Therefore we multiply by the bulk density to convert the hydrogen concentration from a mass basis to a volume basis. Okay, so in this table we can see how the hydrogen index changes from different reservoir minerals and different fluids. So again, we have to remember that the neutron log is mainly responding to the hydrogen concentration per unit volume, right? As we said before. So materials that have more hydrogen that's gonna make us lose a lot of neutrons in the process of absorption, and it's gonna create a stronger like response, right? And the pure water is our reference material. So by definition, water has a hydrogen index of 1. And this is very important because like neutron porosity logs are commonly calibrated assuming water field porosity. Oil also has a hydrogen index close to 1. It's about 1.003 as we can see in the table. Almost the same as water. But like methane and gas are different because, I mean, although they contain hydrogen, their density is much lower than liquids. And since hydrogen index depends on hydrogen per unit volume, so gas is going to have a much lower effective hydrogen concentration in the formation. And that is why in gas zones we can see the neutron porosity reading a low porosity value. In the case of minerals, for example, quartz and calcite, we can see in the table that the hydrogen index is equal to 0 because in the formulas of quartz and calcite, CiO2, SiO2, and CaCO3, we have no hydrogen in this matrix, the structure. So the clean mineral matrix is not contributing to the neutron hydrogen response. But in the case of other minerals like gypsum, for example, it's different because the formula is CaSO4 and 2H2O. So gypsum has water in its crystal structure. So because of that, we can see that the gypsum hydrogen index is not 0, is 0.49 actually. So this is a good reminder that hydrogen is not always the only thing that is affecting the reading. You know, it's not always only the pore fluids. It can also be part of the minerals or bound water that is contributing to or affecting the concentration of hydrogen. And so the point that I want to make with this is that let's say we have a clean limestone with 0 porosity. So if we have a pure clean limestone 0 porosity, the hydrogen index is going to be 0 because calcite has no hydrogen at all. So, and if we have 100% water in a zone with 100% water, the hydrogen index is going to be 1. So if we have a clean limestone fully saturated with water that has actually a porosity, then the hydrogen index is going to be directly proportional to porosity. So let's say if a clean water filled limestone that has 20% porosity, the neutron tool should approximately see a hydrogen index of 0.2, and this is why we can see that the neutron log can be displayed in porosity units. But this relationship only works when we have perfect and ideal conditions. But as we know, in reality, in a real reservoir, we have the neutron response is going to be affected by many things. Like it's going to be affected by gas, light hydrocarbons, Clyde water, gypsum, like organic matter, other minerals that have water in their structure, crystal structure. So this is very important. Like we have to never forget this. Like neutron porosity is not measuring pores directly. It's measuring hydrogen and then converting that response into an apparent porosity. Is apparent porosity. It's not real porosity.